Welcome to today's class. In today's lesson we're going to be talking about integration, which is essentially the opposite of taking the derivative. The second part of calculus we cover in this course is antidifferentiation, or the indefinite integral. We'll be talking about the definite integral later as well. What is antidifferentiation? It's the reverse process of differentiation. Here's our critical question with antidifferentiation. Given the derivative f dash of x, what must the original function have been? For example, if the derivative f dash of x is 2x, then f of x could have been x squared. That's one possible expression. If we differentiate this, it would be 2x to the 1, which is 2x. So there's a possible expression. Are there more? Yes. If our function f of x is x squared plus 5, our derivative is 2x. If our function is x squared plus 3, our derivative is 2x. If our function is x squared plus 10, our derivative is 2x. In each case, if we started with the derivative, f dash of x is 2x, we get a different starting function, plus 5, plus 3, plus 10. Notice, these are the constants. The derivative of a constant, either 5 or 3 or 10, is 0. So if we start with f dash of x, if we're given f dash of x, we have no way of knowing what the constant was. We can say that if f dash of x is equal to 2x, then the original function f of x must be x squared plus c, where c is an element of the real numbers. More generally, we can say given dy dx is some function f dash of x, then the original function y must have equaled f of x plus c. F dash of x went to the original function plus our constant, which we don't know. Let's now talk about the language and notation of integration. The set of all antiderivatives of a function h of x, that's small h of x, is called the indefinite integral of h of x, and is denoted with this curly s sign, h of x dx. This dx is something I see a lot of students forgetting to write. It's part of our integral. The big S is called the integral sign. The h of x is the integrand, so this is your integrand. And x, of course, is the variable of integration. So putting it all together, we have the integral of h of x dx is the original function, or some function, capital H of x plus c, where c is a constant, and that's part of an element of the real numbers. Now that we know that the indefinite integral is taking the antiderivative of some function, how do we find it? Well, here is our original function, x to the n. If we want to integrate it, our first step is to add 1 to the exponent. So we have now x to the n plus 1. Our second step is to divide by the resulting power. So x to the n plus 1 divided by n plus 1. And that's going to be our result. X to the n plus 1 divided by n plus 1. We can do an example of that. What if I have x to the 4? Well, in my first step I get x to the 5. In my second step I get x to the 5 divided by 5. And that will be my result. X to the 5th over 5. Or you could say times 1/5. Compare that to taking the derivative. If I have x to the 3rd and I want to take the derivative, I have to do 3x to the 2, which is multiply and subtract. With taking derivative, I'm multiplying out front and subtracting. That's taking the derivative. If I want to take the integral, I have to add and divide. Taking the integral involves adding and dividing. Taking the derivative involves multiplication and subtraction. It's important to remember that and keep those straight. So if I'm going to take the indefinite integral of x to the n dx, remember you have to have that dx, I'm going to get x to the n plus 1 divided by n plus 1 plus c. In the more general case, if I have some constant a coefficient multiplying by the x to the n, I'm going to get a x to the n plus 1 divided by n plus 1 plus c. It's important to remember that in both cases n cannot equal -1. Because if n equals -1, I really have 1 over x, and that's going to give us our natural log situation. And this will be a over x, and that will also be we'll be talking about the natural log situation.